All right, guys, I want to talk a little bit about some of these questions you had from the homework. In particular, I want to talk about question 13 again, just real quick. Also talking about 14, 17, and 20, and I think 21. These are the questions that I got back from you guys that you want to talk about. But the first one I want to talk about, like I said, was 13. We talked about it in class, but I wanted to show you guys Desmos. And again, you can see here, just go to www.desmos.com. Walk through the kind of tutorial, I guess, on how to get into the calculator. I think there's a button I think says just start graphing. You can download it and all that kind of stuff too, but I just use the web app. Basically, it's just like your graphing calculator. Over here on the left hand side, you're gonna type in like y1 and y2. So you'll hit X. I'm going to do this problem here. Okay, so if you're following along, maybe you want to write that down and then go back to the video. But I'm going to do that equation. So it's X cubed. Now I got to get cubed. A couple ways you can do it. You can hit the caret key, which is Shift 6 on your keyboard. I'm going to go 3. Another way to do it is to actually use their predefined functions down here. Now they got it's squared, so you put squared in, but then you can hit your left directional key and it'll get you back up to the exponent. So you can delete it then and push 3 if you want to. But then I'll go plus 9x squared. Okay, and that's the cubic. And then the other one was negative x squared plus 6x plus 7. And there's the quadratic. Okay, so this is similar to what maybe we saw on our graphing calculator, the TIA 384, in the fact that the window's all messed up. Okay, but what's really nice about Desmos is you can change this window pretty easily. All right, all I have to do is click with my mouse. It's a lot easier with a physical mouse instead of your touchpad on your computer. But I can click and I can move this all I want. Okay, I can zoom out with my my scroller on my mouse. Okay, and I can see now that scroll out real far. This is kind of what that cubic was looking like, that orange function, and then that blue or purple one is the quadratic. So we see that we have these intersection points. Now, to find those intersection points, it is so much easier than what the TIA 384 does. All I need to do to find those intersection points is really just click on one of the two graphs, and you see that it will highlight that point right there, and it's 1.11, which is what we found algebraically in class. It also came up and found this one here of negative 0.6. And then if I scroll down, I'm going to scroll out, zoom out, scroll down, come down here to where my other intersection point was, and just click on one of the curves again. Should put a point there, negative 10.51. And I believe you can probably go into your settings and somehow maybe adjust the rounding tool. I'm not 100% sure. I don't deal with this tool a lot, this graphing tool, but it is convenient. So we get those solutions, and then obviously you can see then once I get those intersections, where is the orange one above the blue one, and vice versa. But that Desmos.com is a good calculator. I think it's a good tool for you to be able to use. And to be honest with you, I don't really care if on a test you want to use this over the top of your TI-83 or 84 if you prefer it. But what I do want you to know is that the reason we talk about the TI-83 84 in class is because that's all that's allowed to be used on the ACT, and that's again one of the reasons for using it in this course is so you can develop some proficiency on the ACT. Now let's get into question 14. Somebody had a question about. Here it's asking us to just identify the domain and range. Remember, the domain is just the x values. Okay, so just the x values that we would come across in this picture. Okay, so what I like to do, kind of visually, I don't actually do this every single time. I do it in my mind. I'm not saying it's the right way, but basically what I do is I take a line, vertical line, and I just start running it through my graph. And the first time I run it through my graph and I intersect my graph, I realize that there's an x value right there that is going to be This point right here is going to be what, negative 1, 2, 3, negative 3, 2. Well, running this vertical line through my graph that way kind of gives me a visual that negative 3 is going to be the first x value that becomes part of my domain. And now as I keep running that through, all of these x values between negative 3 and negative 2 are going to be part of my domain. Everything between negative 2 and negative 1 are going to be part of my domain. Everything between negative 1 and 0 are going to be part of my domain, because no matter where I will get at the intersection of the black line and the red curve, I will get an ordered pair, and the x values that are in any of those ordered pairs will somewhere be between negative 3 and 0. But they'll also be between 0 and 1, and they can also be between 0 and 2. Okay, so I'm looking at x values. Okay, if I were to list all the ordered pairs for this red curve, the x values, the smallest x value will be negative 3. And then I'll use every x value between negative 3 until I get to the largest x value of 2. So negative 3, 2 is going to be my domain. Okay. Now I like to do the exact same thing when I do range, but instead of a vertical line, we're going to use a horizontal line. So now I'm looking at the y values. Okay. So when I go through here, okay, that's going to be the first point that my line intersects, and the y value, that ordered pair obviously is 0 and negative 1, but the y value is negative 1. So the first y value I come across is negative 1. Pass through, and I'm going to get a bunch of ordered pairs. And in this case, I'm getting 2 ordered pairs, but their y values are going to be the same. So like negative 0.5 exists as a y value. 0 is going to be a y value. Everything in between is going to be a y value. I go up to 1. All those values are going to be y values. I keep going. And right here, maybe you think we have an issue, but 2 is going to be a y value there. It's going to be a y value there. It's going to be a y value there. That's fine. So everything so far has been part of my domain from negative 1 up to 2. And then I keep going, and my horizontal line is still intersecting my red curve. So I'm still getting y values between 2 and 3, and I get up to 3, and then after 3, and if I'm here, I have no y values. I don't intersect the curve. So my last y value that I would have gotten as my curve intersected by my black line is 3. So my smallest y value was negative 1. My largest y value was 3. And that's how I think that visually you want to deal with your domain and your range in kind of a similar manner. But the idea is if I took the infinite number of ordered pairs and wrote them down, and then we just classified all the x values, when we looked at all the x values, all of them are going to fall. You're going to have one that's got a negative 3, you're going to have one that's got a 2, but all the other x values are going to fall in between those. Okay. Same thing for the range. You're going to have one y value that's negative 1 and one y value that's 3, but all the other y values for those infinite number of points are going to be in between negative 1 and 3. All right. So this is visualizing a number line left to right. This is visualizing a number line bottom up. Okay, so you start at the bottom at negative numbers and you go up to positive numbers. The next part asks you to determine where it is increasing and where it's decreasing. Okay, I think the best thing to first do is determine where your maximums and minimums are. In that case right there, that's a max. Okay, now we called it a local max earlier in the week, and it is, and that's going to be a local minimum. Okay, but now what is nice about things here, and again, that is going to be a local max, and this is going to be a local minimum. Okay, and because we're looking at a closed interval here, the endpoints are max and mins, and they're going to be local. Okay, if I look at just a small region of values, look at all those ordered pairs that I just colored blue. If I look at all those infinite ordered pairs, this one here at x being negative 2, y being positive 2 is going to be the smallest, basically the smallest y value in that neighborhood of ordered pairs. And that's what we're looking for. When we classify something as a maximum or minimum, we're looking at the y values. The f, maybe if this function is f, we're looking at the f of x values. But now, when we find our local maximums and minimums, and mostly when they're like peaks and valleys like these two, they help us define where our function is increasing and where it's decreasing. So when we look at this thing, there's a change in behavior. There's a transition at these maximums and minimums. So at those points right there, okay, from 1, 2, 3, -3 up to an x value of 1. So -3 to 1. And we're gonna let's just use open intervals here, okay? Because if I close it and I'm just looking at x being -3, and I don't know if I like that idea. So we're gonna use open intervals. We're gonna go from -3 to, I guess it's -1, is where you're increasing. Okay, the graph is going up, and then what that means is that from that point there to that point there, your y values got bigger from one to the next, going from left to right. Okay, and that continues to happen. If I look at now that point and that point, still my y values are getting bigger, and I can keep doing that until I get to that point right there, and that's kind of that's the very tip top. It's the maximum, and then everywhere after the maximum, I'm going to start decreasing again. Okay, so between, if I color them blue here, those y values, every successive pair of y values, one after another from left to right, they're getting smaller and smaller. So between -1 and 0 for my x values, we are decreasing. All right. Then we start to, at that point, at that minimum, we start going back up again. All right, so that's increasing. So that's going to go back up from 0 to an x value of 2. All right, so these were my increasing domain values, and these were my decreasing domain values. And that's how we write these things. When we're asked where is it increasing and where is it decreasing, the question really is asking for what x values are the y values increasing. And this is for what x value. These are those x values that we say for what x values are your y values increasing. So on these x values, our y is increasing. And on these x values, our y is decreasing. Okay, so that's how you kind of deal with question 14. Question 17, very similar question. I don't want to do this one because it's a piecewise function and it's got some maybe domain issues that we want to think about. But again, just putting that vertical line in here. All right, so start putting that domain idea through that line, traveling it through my curve. And the first place I intersect is right there. So that x value is 0. So I have, in my domain, I start at 0. Okay, and I'm going to have an x value there and there. Okay, my black line is intersecting my red curve again everywhere. And then I get here. Okay, and there's an issue because there's an open dot there, but there's a closed dot there. So if I were to write all the infinite ordered pairs so far that I've traced through, one of those ordered pairs is going to have an x value of 1. Okay, basically this open dot says you're going to have an x value of like 0.9999999, as many times you can say that. And then because it's closed here, it allows you to also make the transition from that 0.999999999 number to the next number, which would be 1. Okay, so there we don't kick any numbers out. Okay, the domain is still from 0 to 1, and then we keep going and we keep going and keep going and we get to 2. So we got 0 to 2 so far, and then we come to an issue right here again, but for the same reason. You've got an open dot right there, but it's closed right there. So an x value of 4. Or sorry, 1, 2, yeah, 3, sorry. An x value of 3 would show up in your list of ordered pairs. And then keep passing it through and we get to 4. But after I pass an x value of 4, my black line doesn't intersect my curve anymore, so we stop at 4. Okay, so now we're going to do the horizontal one. So my smallest y value I come across right there, we intersect right here, would be -2. And now I'm going to move this line up, still intersect twice, but that's okay. Okay, we get to this point here, and we got an open dot there, an open dot there. So those open dots tell me that we would not have a y value at 1, but because there's basically a closed dot there, we do have a y value of 1, so there's no issue there. Okay, so we still have y values from -2 all the way up to 1, and then we're going to include 1 and keep going up, and our last y value we get to is 2, and we include 2. So this was my domain, and this here was my range. All right, they asked for intervals of increasing again, so increasing and decreasing. So I'm just going to, kind of go left to right with all this stuff. If I look at this piece, okay, if I travel across the x-axis, we're asking again what x values are or y values going down. So from 0 to 1, your y values are going down. But when I get to 1, there's a transition here. Now the transition says that everywhere I go from 1 this way, my y values are going to get bigger and bigger. So from 1 to 3, okay, this little range here, or this little region here, that's increasing. So I'm going 1 to 3 is increasing. And then hopefully we recognize then right there from 3 to an x value of 4, you're decreasing again. So 3 to 4, decreasing, and we union those. Okay. So 17, 20, similar idea. 20 is asking for max and minimums first. So there is all our locations for maximum minimums in this particular problem. And they're asking for local ones, okay? And then they come over here and they tell you, like, type in the smaller of the two or something like that. So it tells you which one to type in. But this one here is at 1, 2, 3, -3, 1, 2, 3, 4, 5, 6. So -3, -6. This one here is at 0, 0. This one here is at 3, 1, 2, 3, 4, 3, -4. And this one, if that's 3, 4, 5, 6, 2. All right, so looking at these, okay, because we go from decreasing to increasing, we got a trough here or a valley. That is a local minimum. This one here, we got a peak, okay, or a local maximum. This one here is another trough, so that's a local minimum. And this one here is a local maximum again. Okay, now in regards to like questions where they ask for like global maximums and global minimums, none of these are global maximums or global minimums because there's points, because this goes on forever. So there are values up here that are bigger than any one of these maximums. Okay, and for the same reason, this goes on forever in that direction. So there are values over here, y values over here, that are smaller than any of these minimums. So there are no global maximums or global minimums on this curve. It would be different if they put a point there and a point there. They truncated the curve, cut it off, shortened it, whatever. Now that would be a global maximum, and that would be a global minimum because they're y values that are either bigger than the rest of the y values, or they're y values that are smaller than the rest of the y values. Remember, when we talk about local maximums, we're really just talking about the y values that are kind of in that neighborhood, or the y values that are in that neighborhood, or the y values in that neighborhood, or the y values in that neighborhood. But when we talk about global, we're looking at y values. That y value may be compared to every other y value in the graph. But if they don't put a point here or a dot, we assume that those go on forever. The next part they ask you is can you find the range, or the domain values, I guess, the domain values, the x values, for which the graph is decreasing. So I'm going to go through and just find my decreasing. I'm going to write decrease and increase. And as I go from left to right again, hopefully you realize that we are decreasing over here. And so this goes on forever. So the first value to come across would be -infinity. So going on forever, -infinity. Are those x values that we're decreasing, and we get up to an x value of -3 right there, and we're decreasing all the way up to it. But at -3, we transition. That's why they ask you to find these minimums and maximums first, because we transition, and now you start to increase. So from -3 to 0, you start to increase again, and we get to that point, that transition. Now from that transition to here, okay, and it appears as though I've made a mistake because they've got a 2 here. I guess everything I've been doing so far has been referencing that to be a 1. So really, this should be, 2, 4, 6, 8. So basically all my numbers should be double what they are. I'm gonna continue doing this, and this is my mistake. I apologize. I'm going to continue doing this as if that's a 1 right there. So 1, 2, same thing here, 1. That's something to pay attention to on your scales when you're doing your assignment. But if those are ones, you're going to start decreasing from 0 to, in this case, 2. 0 to 2. Tell you what, let me start the whole problem over. I apologize. Okay, so question number 20. They're asking us to find local maximums, increasing, decreasing. Same idea as what the last question was. Pay attention though, and I did this whole problem once already, but I did it wrong because of these intervals here. So that's 2 and that's 2. So that means that's 4, 6, 8, 10, and so forth. So this point here is actually 10, 4. This point here is 4, 2, 4, 6, 8. So that's 4, negative 8. We got 0, 0, and we've got 2, 4, 6. So negative 6. And then if that's 8, 10, 12. So negative 6, negative 12. What they're asking you to do here is to identify these as local maximums and minimums. And remember, a local maximum and a local minimum, if it's a trough like that, it's a minimum. So local minimum. If it's a peak like that, okay, it's a local max. Again, local minimum there. And up here, a local max. Now, the logic or the reasoning is, if I look at all the ordered pairs here that I've made blue down here in this little neighborhood, negative 12 is going to be the smallest y value I ever come across in all those ordered pairs. So that's why it's called the minimum. Okay, it's the smallest y value that you get. Same thing for the rest of this. That 0 right there is going to be the largest y value that you see in any of the points in that neighborhood. Okay. Now in this particular graph, we're going to interpret that this goes on forever in both directions. So there are no global minimums and global maximums, or absolute minimums or absolute maximums, because when we think about global, we're taking a particular y value and comparing it then to every y value on the curve. In this case, any y value you choose, there is going to be something bigger than it. Even if we choose infinity, because infinity 1 plus 1 is going to be bigger than that infinity. So no global maximums and minimums on this. But however, if we would do this, if we make that a point and say we've cut our graph off, this would be a global max. Because that y value of whatever 2, 4, 6, 8, that y value of positive 8 would be bigger than any other y value on this entire curve. Okay, even if we just continue, let that one continue to the negative. So just cut just this portion off. Okay, but for this problem, no global maximums, no global minimums. The next thing they want you to do is to find out where this thing's increasing and decreasing, and the reason they do this in this order is once you find your maximums and minimums, those are the transition points for increasing and decreasing. So reading left to right, okay, until I get to this first local minimum, if we have a minimum, that means from the left of it, you are decreasing, and then to the right of it, you're increasing. So from negative infinity up to negative 6, my graph is decreasing. My y values are getting smaller and smaller as I go left to right. Now, as I go from negative 6 to 0, my curve is rising. My y values are getting larger. So we're increasing from negative 6 to 0. But now if I go to 0 to 4 again, we've hit this maximum, Once you hit a maximum, you got to go back down. Okay, so we're going from 0 to 4, going back down along the graph. So 0 to 4 is decreasing again. And then I get from 4 to 10. Okay, so from that x value of 4 to that x value of 10, your graph, your y values are getting larger and larger. So 4 to 10 is increasing again. And then 10 to infinity. 10 to infinity. Let's see here. 10 to infinity, we are going back down. Y values are getting smaller and smaller, so we're decreasing. And then we just want to union these things. I think even on the website you can put commas in. But that's the logic. That's the idea behind this type of problem is to find your local maximums and minimums. They're the transition points for increasing and decreasing. 21, same concept. I'm just going to real quick look at that point, look at that point, look at that point, look at that point. My eyes are drawn there because those are troughs and valleys, or troughs or valleys, how you want to refer to them, and then you got your peaks as well. Okay, so trough or a valley here, trough or a valley there, peak, peak. Peaks are minimum or maximums, troughs and valleys are minimums. So some max, min, max, min. They're all local because, again, going on to infinity in both directions, there are y values that are smaller than that one there. There are there are y values that are maybe bigger than that one there. Okay, so then I'm just going to kind of highlight just to get through this problem a little bit quicker. If we look at those values right there, it's a terrible job of highlighting. If we look at, let me do it, hold on a second. Do this. If we look at those y values, okay, in that yellow region, they are increasing. Okay, so when we're asked the question if they're increasing, we write the x values for which they're increasing. So my x values for increasing right now for negative infinity up to, now they're saying we're jumping by 3, so negative 3, negative 6 would be the first domain interval for increasing. I'm also going to see that I am increasing there from 0 to, again, 3 and then 6. So 0 to 6. And then again over here we start increasing again. And that's going to be from, what, 3, 6, 9. So 9 to infinity. All right, so we union those. And again, that is when our y values are increasing. Decreasing would be everywhere that I did not highlight. So decreasing would be from negative 6 to 0. Negative 6 to 0. And then from 6 to 9. What's kind of neat about this is that if we've done this correctly and this graph is continuous, think about this thing here as a number line. This set of numbers should go right between that interval and that interval, if we picture it as a number line. And this one here should go right between those two if we picture this as a number line. And that will then give us a one solid continuous number line. So if you know where it's increasing and the function's continuous, you should automatically know by default where it's decreasing. Might be a kind of a trick to help you to do these problems maybe a little bit quicker. Make sure that when you're finding the local maximum and minimum in this one, and you see the answers here, but you're counting by 2's on the y-axis. I think that's something people struggle with. Is that they look at the graph right away and they start want to go, 1 to 1. This is 2, 2, but realize how they're using their scales here. And this one's kind of a pain in the butt because they're different. Okay, so just pay attention to that kind of stuff.